Hello and welcome to part 9 of this series of videos on the introduction of the mathematics of signals. For a playlist containing all the episodes, please see the link at the top of the screen. This episode will introduce the discrete time Fourier transform and the FFT, the Fast Fourier Transform algorithm. So here's a quick outline. We're going to try and answer questions such as: how can we apply Fourier series, which were introduced in part 7, to sample data, as we saw ages ago in part 2. If it's forgotten that bit, you might want to go back and watch some of that one again. What are the consequences of this data being sampled? What's that going to do for the Fourier series? And how is this data organised when using the common Fast Fourier Transform algorithm and the implementations you often see? So the starting point here is, like in part 2, whether signals are continuous in time or whether they're sampled. That's the basic difference we're looking at now compared to the last couple of parts of these videos. And what we're seeing here, like we saw in part 2, is a continuous time signal. We've sampled that at a discrete sort of list of sampling times, TK. These are regular sampling times with a sample spacing delta t. Equivalently a sampling frequency Fs is 1 over delta t, and that gives us a discrete time signal xk, which is just a sequence of the values, the instantaneous values that x has at all these times tk. So hopefully that's familiar. If it's not, if it all seems like a very long time ago or you didn't watch that video, then go back and find the part 2 video and watch that again. The other thing that we discussed in the part 2 was the idea that you might have a sampled spectra. So you might have a continuous spectra, which is the sort of light blue line, and then you might have sampled that to these different points with the stems with the crosses to give you a sampled representation. And this, if you've been watching the last 2 parts of this video, particularly part 7, which dealt with Fourier transform, and then with the Fourier series, we've got the continuous spectrum XD from the Fourier transform, and then you've got a discrete spectrum you might get from a Fourier series XN, and that's like x of d, the continuous one evaluated at xn, more or less. So actually we've got some regular sampling here, and that as we've seen is, I mean, in part 2 I introduced it as how you might plot a spectrum based on data in an array, but we now see that actually that's really compatible with Fourier series. So Fourier series is where it's going to start. Now what I'm going to do in this part is just try and talk about the difference between some of these different sort of flavours of Fourier transform as we've been talking about them, because much like you saw for some of the previous videos, Fourier series really boils down to 2 equations. There's quite a lot going on to understand them. Fourier transform boils down to a pair of slightly different equations, and we'll see that the discrete Fourier transform also boils down to another similar looking pair of equations. But all of them have got various different assumptions built in, and it's really understanding those that is the key part. The assumptions are just, the equations are just the sort of compact way of writing what's going on and how to do the computation. So Fourier series, first of all, we've got continuous data in time, so we've not got sample data in time, but we have this periodicity assumption. We assume the signal repeats every time t. And what that gives us is it gives us a spectrum that is sampled, that's only got lines in it. And I haven't managed to draw this with the beautiful stems and crosses like I had in the last slide, so we've got this sort of slightly just lined kind of pattern there to represent a sampled spectrum. So we just got the values at these xn. So let's try and build up a summary slide, flavours of Fourier transform. So Fourier series assumes a signal is periodic with time t. It's going to be a continuous time signal, and it's going to give us complex amplitudes xn at discrete frequencies, so it's like a sampled spectra. And the frequencies those are at are related to the time period t. The forward transform operator is an integral, the reverse is a summation. Then we saw the Fourier transform, and that manages to eliminate the time periodic assumption by taking the limit as t goes to infinity. So the signal now never repeats. So in part 8 we saw this slide where we had a signal and we said how much of this time are we considering to be repeating, and then we said what would Fourier series give us as its spectra, and we get a set of lines, but as t gets longer these get closer and closer together because the spacing is defined by 1 over t. So if this doesn't look familiar, go back to part 8, go and find that and have a look and watch that one. And after you do this and you kind of take the limit as t goes to infinity, and you deal with a couple of the normalization terms that we were talking about, what you get is a continuous signal to a continuous spectra. Both of these are non-repeated, they don't periodic in any way, and they're both continuous. So this is actually kind of when you're thinking of signals in the real world, what you're often thinking of, because signals in the real world are continuous, and spectra in the real world are basically continuous as well. There's nothing to say that a machine can only produce a tone noise that's like 1000 hertz or 1001 hertz or whatever your spacing of delta f might be. Sounds can contain any frequencies potentially. So Fourier transform's the sort of most abstract mathematically, but it's also in a weird sort of way the most realistic. So let's go back to our summary slide. So flavors of Fourier transform: the signal now never repeats, but instead of a set of discrete complex amplitudes, we're going to get a complex amplitude density xd. That's what the d was representing for any frequency f, not just one of these Fourier series frequencies, any frequency we care to think about. The downside is that both operators are integrals running from minus infinity to plus infinity, so while this is sort of more representative of the real world, it's not something you can actually compute. But finally we have the discrete Fourier transform, and a bit of a misnomer as far as I'm concerned. It's a Fourier series for sampled signals, and what we're now having is that the signal, as we saw on that very first slide, is a sequence of values. Xk is x evaluated at tk for discrete times tk is k delta t, so they're evenly spaced, regular sampling. So what might this work like? So let's start off, and we've got a continuous time signal, and we've got a discrete time signal, and we've got regular sampling. We've got a sample frequency fs is 1 over the spacing between the sample times. So those are all the bits about the fact that this is a sampled signal. Then on the right we've got the stuff to do with the fact it's a Fourier series. So we've got some Fourier series frequencies. Fn is n delta f, where delta f is 1 over big T, the period, and that is the period. And now we start to relate the two things together. We're going to say, well, hang on a minute, this is sample. We're going to have to make this period a fixed, so integer number of samples. So we'll say it's n times delta t. And actually, if you just put n delta t into the thing with delta f, then you can just sort of combine those two equations above and show that delta f times delta t is 1 over n, which will prove useful in a little while. So first of all, let's start with the synthesis, the reverse transform, which is always the easier one, I think. And this is a summation. And what we're going to do with that, well, we're going to put in our definition for xk. So we're going to say, well, we're going to just only be able to evaluate this at x. We're going to put in our definition for xk. And we're going to say we only want to evaluate this at tk. So put that in, and we find that xk is just this evaluated at tk, and all I've done here is into the exponent there, I put that tk is k delta t. I've also put in the definition of the Fourier series frequency, Fn is n delta f. And then I could just use this last thing, delta f delta t is 1 over n, and they all sort of drop out, and I get this statement here. And this is the discrete Fourier transform, reverse transform. That is it. So that's all the steps. We've just put in the definitions, and it kind of fell out. So the reverse transform is really straightforward. The forward transform requires a little bit more thought because that was an integral and we can't really do integrals on discrete data. But again, we already talked about this in part 2. We've got a continuous signal, we want this integral. But what we actually have is this sequence of samples. It's like, well, okay, they're spaced by delta t. So let's turn each one of those into a little rectangle that has area that is delta t times whatever height, whatever sample value it was. And by realising that that's going to approximate this area under this curve and the integral, we can say that, well, actually, we can approximate an integral by a summation of all the samples multiplied by delta t. Okay, great. So we'll basically just plug that in. So where we had an integral before, we're going to say that's roughly equal to delta t now over big T, because we had this delta t multiplying factor out on the right, and we've turned it into a summation over samples instead. Of course, 0 to n, well, n minus 1 here, because there's n samples repeating. And then we're going to do what we did before. We put in the definitions for fn and tk, so we just end it with delta f and delta t in the exponent. And then finally, I'm just going to do two other things. I'm going to notice again that delta f delta t was 1 over n, so get rid of those. And out the front we had that delta t over t. I realise that that's actually also related to n, so I get 1 over n there. So that is it. So let's put them both on one side as a little summary. So we had all these parameters here to do with the sample on the left hand side and to do with the Fourier series on the right hand side. That was from the previous slide. But if you look at the actual equations that have come out, you find that hardly any of those matter at all. They don't crop up at all. In fact, the only one that crops up is n. So they can all be forgotten really. And in terms of the actual numerics of this, the only thing you need is the number of samples in the sequence. And of course, that's why you find that these FFT algorithms only have one argument, which is the sample of the list, the array giving you all these samples, because it can work out n from the length of what you give it. So you don't even need to tell it n; it can figure that out for itself. So you just give it xk, a list of them, and it spits out xn, or vice versa. So that's why you'll see FFT and IFFT algorithms called with no other arguments whatsoever. So that's the numerics. Those are the statements. As I said, we're just going to get another pair of statements that work together. But again, there's quite a lot going on, and we need to just understand a few more of the similarities and differences. So let's just think what happens. We had a Fourier transform here, going from a continuous time non-repeating signal to a continuous spectra. What happens if we make this sampled? Okay, so now we've taken away some information. We only know the signal at a set of sample times, not all the time. We can't interrogate it and find out quite as much information as we could before. So this is going to introduce some ambiguity somehow. And basically what it allows is aliasing. And many of you may have heard of this. So if you take a tone and you sample it, there we go, you can find that there's other frequencies that will go through those points. And they have a special relationship. They are the frequency you put in plus or minus integer multiples of the sample in frequency. This relationship of how far apart those sampling times are. And if you put f plus fs in there, you'll see that one go through all the points. If we put f minus fs in there, you'll see that go through all the points. If I put f plus 2 times fs in there, it gets all a bit kind of crazier and faster. They're oscillating, but it definitely still goes through all the points. So you get this ambiguity that there's different frequencies that could go through that same set of sample points. So what we find is that simply by merit of sampling that data, we get copies of that spectra spaced repeatedly by the sample frequency, and we don't know which one of those it is. There's ambiguity. You could say that it was one of them, or any of them, or all of them. It's a periodic spectra. So much like in Fourier series, we had a signal that was periodic in time, which gave us a sampled spectra. Now we've sampled in time, and we've got a periodic spectra. But actually, of course, what we're doing is sampling is going to implement a Fourier series. So actually, we've not only got a sampled signal, but we've got one that repeats. So we're going to get a repeating signal at the top, and all those spectra I had at the bottom are now also going to be sampled as well. Remember that our two operators, these two equations on a couple of slides ago that gave us the reverse and forward discrete Fourier transform, they do a sequence to sequence of samples in the time domain to sequence of samples of a spectra, and that is exactly what we're getting here. And I always think it's a bit unfortunate it's named Discrete Fourier Transform, because it is actually from an audio point of view implementing a discrete Fourier series, but that is the name that it gets. Sounds a bit cooler maybe as well. So just to surmise here, the discrete Fourier transform is a Fourier series for sampled signals. The signal is a sequence of values at discrete times. And we're going to get complex amplitudes out at discrete frequencies as well. And both operators are now summations. And the FFT, Fast Fourier Transform, is not a different thing. It's just an algorithm that computes it fast. So let's look at another way of summarising these relationships. That's on this diagram here. So on the top right, I have the Fourier series, which is the first thing that we met, where we have continuous signals in time, but they are periodic in time. And that means that the continuous nature in time is going to mean we're non-periodic in frequency, so we've not got this sort of repeating spectra thing I mentioned a minute ago. We've got enough information in time to be able to be confident about those frequencies. There's no aliasing possibility. But the periodic time gives us a discrete frequency spectra, a sort of line spectra. On the top left we have the Fourier transform, and now we've got a continuous time signal and a continuous spectra, both are non-periodic, non-repeating, and that is probably a bit more like the real world in a way, but the penalty for that is that it's got this rather abstract mathematical form with infinite integrals, which you can't really do anything with numerically. And then down the bottom we have two different versions. We have the discrete Fourier transform I just talked about, which is this algorithm you implement the FFT, and that goes from sequences of sampled data in the time domain that are periodic to sequences of sampled spectra which are also periodic. So we've got sampling and periodicity in both time and frequency domains. And then just to complete the picture, we have this discrete time Fourier transform, which is a Fourier transform for an infinite length signal, with sampling, and that would give you a continuous spectra there with no lines because you had an infinite signal and time to look at. But the the sampling would give you the possibility of aliasing, and therefore we get these periodic spectra. Now, that's not really used that much, to be honest with you. If we just go through how you might actually work with these, so Fourier transform is definitely something that you do by hand on paper. Fourier series is mostly something you would do by hand as well. You might plot a graph of it or something, but generally you'd have to do that by hand. Discrete Fourier transform, that's the one where computers come in. You've got sequences of time data, sequences of spectrum data. That's what computers are good at. And this one on the bottom left is not really used. It's more of a kind of mathematical construct. It's impractical. You've got sequences of data which you could evaluate on a computer, but they're infinitely long, so you won't have enough memory, so you can't do anything. So that's kind of ruled out. And what we're really interested in is getting kind of between these three here, because the Fourier transform, as I say, is the one that's a bit most like the real world, and the discrete Fourier transform is the one we can evaluate on a computer, and we kind of have to go via the Fourier series to understand the difference. So I'm just going to kind of do that on this last couple of slides, just look at the differences between these. So we'll start at the Fourier series, and so this is the two equations for this. This equation's going to have a lot, so this slide's going to have a lot of equations on. I apologise, I'm trying to surmise the differences here. And at the top we've got Fourier transform, which we met last time. We'll get some different equations there to evaluate that. I won't focus on those, but I'll just point out that the sampled data given by Fourier series is related to the data that you get from a Fourier transform. What should happen is that you're getting the continuous spectra of the Fourier transform evaluated at some discrete frequencies, more or less, with a bit of scaling by this term delta f, because xd was a density, sort of quantity per hertz, amplitude per hertz. Going back down the other way, we come to the discrete transform, going the other way around, and this is the thing that we've just met. Now we have sequences of data, both in terms of like a periodic spectra coming from the Fourier series, so a sampled spectra coming from the Fourier series, and we get sampled data coming from the sampling in time as well now. So the main difference here is that our data is now sampled, so there's the relationship between those. That's quite straightforward. And we have this factor that actually between these two domains, between the harmonic frequencies and the time period of the Fourier series and the sample frequency and the sample period of the sampling, we just got this relationship of how many samples fit in a repeat period. That's the most important thing, n. And then finally, you've got algorithms that might implement this, and they're not too different. They're pretty similar, particularly if you're using SciPy or some other system where the array is indexed from 0, the n of the array index matches with the n in our maths, and this is all fairly straightforward. The only thing that's quite annoying is that the 1 over n is put in the reverse transform rather than the forward transform is the kind of the standard thing to do here. So it's rather irritating factor that you've got another n multiplied by to worry about as well. The xk's are all right, but the spectral data gets scaled by n. So actually, I think they're all pretty compatible. There's just a lot of little kind of changes all along the way that just can cause a little bit of confusion. Particularly, you know, this thing at the top about Fourier series give an amplitude, Fourier transforms give an amplitude density, and this thing at the bottom, which is just quite frustrating, where you have a discrete Fourier transform, but then actually the algorithms are doing that you get in code are doing something a little bit different to what we'd ideally have them do. And things get a bit more confusing again if you use Matlab, which indexes arrays from 1, so rather than x0, you have xn plus 1. So that's just another little complication, is that n in your sample indexing the array doesn't match the n that you might use in your maths. But Matlab is what we mostly use at Salford for audio at the moment on our courses, so let's just look at that just last of all, just to think about how that data is arranged. So we're going to have these repeating spectra, these repeating line spectra, sampled data but repeats as well. And what you're going to get out is an array like this that's length n. And the first entry, 1, which would be 0 if you were using SciPy, but it's 1 because we're using Matlab, is going to be 0 hertz. Then we have some positive frequencies in blue there. Then we have the Nyquist frequency at f n over 2 plus 1. And then we go all the way up through some other frequencies that are even higher above Nyquist, up to nearly the sample frequency. So n is just not quite the sample frequency. And if you wanted to list these frequencies in Matlab, you would write this. You could write the sample frequency times 0 to n minus 1, all divided by n. And it's just worth mentioning at this point that if n is odd, you would basically omit the Nyquist frequency from this. But of course the spectrum is periodic, so we could also regard these red frequencies as being the negative frequencies copied, and this is how you'll more often see them talked about, is that these are actually the negative frequencies. So they're above because the spectrum is periodic, but you can move them down over here. There's a function called Fft Shift that does that for you in Matlab. And yeah, so now we've got we've got a sort of funny situation. We start from 0, go up to Nyquist, and then loop to the other end and come back from negative, just above negative Nyquist. But the data is all still there, and that's why you understand those as negative frequencies. And if you want that F list, you can build it like this, where you go up 0 up to n over 2, and then you go 1 minus n over 2, so negative up to minus 1, and divide all that by n. That's how you find the frequencies for that arrangement. Okay, so let's get to summary. So The discrete Fourier transform is a Fourier series for sampled signals. The signal is a sequence of values, xk of x at time t and k, sampled at discrete times tk is k times delta t. And this repeats every n samples, or t equals n delta t seconds, because it's based on a Fourier series. We give complex amplitudes out of it at discrete frequencies fn equals n over t, so that matches the Fourier series. But now the forwards and reverse operations are both summations. In terms of the code, both take an array of length n and return another array of length n, whether they're doing the forward or the reverse transform. And the Fast Fourier Transform, which you'll hear about, and people will write FFT as a kind of just another way of saying discrete Fourier transform, but it's not a transform, it is an algorithm that computes it fast. And that is kind of that. I hope this has been useful. As you'll see, the actual maths of what a discrete Fourier transform is quite compact and there's not much to it, but there's a lot of other kind of understanding the differences between these different types of transforms, and I hope that's been helpful. Next time we'll sort of just finish this off by just thinking a little bit harder about those differences and say, well, what happens when you approximate a Fourier transform with a Fourier series computed using an FFT? And that's what I started to look at there, this kind of movement around that diagram of the 4 quadrants, but we're just going to think about that a little bit more. So, thank you.